Alright, so we are going to continue with mobile IPv6. Last time we did v4. So what is the difference from v6? So before that we will just go into what is v6. What is v6? In particular, we'll talk about the extension headers, neighbor discovery, and so on and so forth. Then we go into what is the difference between mobile IPv6 and v4. And then there are 3 or 4 things which are unique to v6. So how many people are familiar with v6 already? 1, 2, 3, 4, 5. So 3 of you who are not familiar, I'm just going to give this brief introduction. We all know that v6 and v4 major difference is that v6 uses 128-bit addresses. And with 128-bit addresses, the first 64-bit are assigned for the network and then the last 64 for the host. And there are plenty of addresses available, so everybody can have a global unique address. I mean global address as opposed to this, so there is no need for any private addresses. So here's the address. So 128-bit total, 64-bit of global routing prefix, 64-bit what we call network prefix, which consists of 2 parts, subnet ID and the global routing prefix. So this is what we call the network prefix, and then this is the host part of the interface ID, another 64-bit. Generally, this 64-bit is made up from MAC addresses. Anyway, so this is there are 2 bits in the middle, G and U. G means it is group ID and U is universal. So this is where a MAC address, if you remember the IEEE 802.3 or 802. Actually IEEE 802, not any point. IEEE 802 addresses are 48-bit addresses, right? The Ethernet addresses. And the first bit is multicast or unicast, group or non-group. So that's where that bit will go. And then U is the universal or local. So in Ethernet addresses, the second bit indicates whether this is an address which was assigned by IEEE, which is universal, or it is assigned by the organization owning it. You can assign a local address. So that is the non-universal address. So those are the same 2 bits here. So 48 bits will fit, and then 8 bits afterwards would be selected somehow randomly, and this first 8 bits. So so let's see, and the addresses are put into a hex :hex notation. So if you remember in the IPv4, the addresses are written as what radix they use, hex or octal or what in v4? Decimal, right? So in v4 we use decimal, and then we put between those decimal numbers what we put? Dot, right? Actually that dot reminds that this is a decimal number because the dots are used in decimal numbers. Here it is a hex and it is colon. So when you see a colon, then you know that this is an IPv6 address with and written in hex. So even though number could be 0, 1, 2, you know that this is a hex number and not a decimal number. And only other notation is that if you see 2 colons, that means you can add enough zeros in those positions to make it 128-bit. So for example, this address which has 2 colons here, now we have specified 1, 2, 3, 4, 5 16-bit numbers. So 5 times 16 is 80 bits are already specified. Now we need to specify missing numbers are 3 more 16-bit numbers, right? So we put 3 zeros here, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that's the notation, and there is one. So that is the major difference, is the address type. Second major difference is that there is an extra field in the packet called flow label. So if you take a source address, a destination address, and the label field, and you combine those three fields, so the source address is 128-bit, the destination address is 128-bit, and the flow label field is, I think, 16-bit. You combine these 256 plus 16 bits, that combination indicates a flow. A flow is something like a TCP and some kind of application or group of applications, and so rather than looking into the port numbers as we do in IPv4 to find out what application it is, you can use just flow level to determine a flow, and not. It's basically, there are certain things that we cannot do to a flow. For example, if we don't want to reorder the packets inside a flow, right? So you don't have to look at the port numbers, you can just look at this flow field. Second thing is, it also has scoped addresses. So just like we have private addresses in IPv4, and the private addresses cannot get out of the organization, they have to stay inside the private region and they cannot get into the public internet. So here they have defined many more such boundaries, not just the public-private boundary. Inside the private network, you could have a link boundary, a site boundary, and so on and so forth. So there is something called link local, an address which is good only for that link, which means on that Ethernet. As soon as it gets out of that Ethernet, the first router will block it. Site local. Site local is it is good for that particular site. So for example, WashU has two sites, medical school and this is school, and then if there is a site local address which will be identified by certain bit in the addresses, that address will only be allowed inside this site and cannot get out of this site. The routers on the boundary of the site will block it. And then they have extension headers. So they have lots of headers, which basically IPv4 has only one header, in which you have source address, destination address, and so on and so forth, many fields. But IPv6 has many headers, and some of these headers are optional, and so you can just use as many headers as you need for whatever application you have. So that the headers, if everything was required, then the header will become very big, and the address by themselves are so big that the header is already big because of just the two addresses. So they said, okay, we will have lots of optional headers. Those are called extension headers. So extension headers could be a routing extension header, hop by hop extension header, and destination option extension header. As the name indicates, the routing extension header is used for routing the packets. Maybe you want to specify source routing. Hop by hop extension header is changed at every hop. Destination option header is only used at the destination, and not looked up along the route. So anyway, it turns out much of this we will not be using, even though this is these features are there, but we might use an extension header or two. But other than that, these are just general introduction to IPv6. Second common thing is in IPv4 we need DSCP. DSCP is the Dynamic Host Control Protocol. What does DSCP do? Assign the address on the IP address on the network, right? So that is allowed in IPv6 as well. However, you can do yourself. You can generate an address yourself and use it. So you don't need a DSCP server, and that is called stateless. Stateless host can make a global address using the advertised network prefix, and then the network identifier should be unique. So basically the interface identifier should be unique. So using their MAC address and the network prefix which has been advertised, you can make up an address which is unique to you, because nobody else has that MAC address. MAC addresses are globally unique by design. So that is another thing, is that you can generate your own address, and it is called stateless because nobody remembers it. I mean, the thing is, in the case of stateful, DSCP has to remember that I assigned this particular address to this host, and in fact, if you reboot your router in the middle of something, the router may assign your address to somebody else. Generally, it doesn't happen, because the reason it doesn't happen is because generally when you request an address from DSCP, you give a preferred address. You say, well, can I get 104? Because that was your address before, right? So, huh? No, the lease is forgotten. The thing is, when you reboot the DSCP server, the lease is forgotten. It doesn't remember that I had given, I mean, unless you have a router which has some memory in it, but most of the routers will not remember what they had leased out. Not over the reboot. They will remember if they are up all the time. But if you reboot them, then somebody else can get the same address, but it doesn't generally happen because the requester has not rebooted. If both requester and the DSCP server is rebooted, obviously this can happen, but then it's not a problem. So the point is that the DSCP server has to remember what address they had given to whom. So it is stateful, and if the state is lost, there can be some conflict. Okay, two hosts may get the same address because one is having the previous lease, hoping that the lease has not expired, and the new one has been given to somebody else. You understand? And so sometimes you get a message on your computer, and I don't know how many of you have gotten this message, but sometimes you get, well, there is an address conflict on the network, right? And that means that your computer has the same address as somebody else, same IP address as somebody else on the same network. And in that case, all you have to do is release the address and basically ipconfig command. ipconfig / release and ipconfig / renew. When you go to renew, you get the new address, which doesn't conflict. Okay, so this is called stateless and stateful. All right. So what is the difference between mobile IPv4 and mobile IPv6? So first thing is that there is no need for a foreign agent. The reason you don't need a foreign agent, because care of address, you don't need a care of address because you have a globally unique care of address. You can make up your own globally unique care of address. So you just basically it comes directly to you. Second thing is route optimization, is that you do not have to go everything through the home agent, because then everything is a triangular. You know, if your correspondent is next to you, you can go directly. Now here it turns out that all of these optimizations can be extended to IPv4. So it's not that IPv4 is missing something. It's just that they're discouraging to make these to IPv4 because so that IPv4 basically goes away. IPv6, there is a reason for it. Come back, yeah.
So the route optimization, doesn't that remove what you had in IPv4 with location security, so that if your route is optimized, so that you just send?
Yeah, exactly. So that's the point, is that, I mean, IPv4 can also do route optimization, but there we didn't do it, and we said, well, we don't want to have local location privacy being violated. So route optimization does violate the location privacy when you do that, but basically you can do it selectively, in the sense that you could do only with the correspondents with whom you want to tell them location. Secure route optimization, and then and we will talk about that briefly later on, is that you could do it so that when you are, one of the problems is if you're not going to go to home address, somebody else could say, well, I am Rajan from Vashu, and then here is my foreign address and so on and so forth, and please send me all your packets. And then somebody wants to say, wait a minute, are you really from Vashu? How do we verify that? So that is the secure route optimization. new extension header in place of tunneling. So tunneling means putting two full headers. Remember, what was tunneling was encapsulation. So you had the IP packet with full IP header, and you put another full IP header on the top of it. That we don't need here because we have extension headers. So we can just add a little extension header, and whatever extra information is required, we can put in there, so it is less overhead. And then neighbor discovery in place of ARP. Now ARP is address resolution protocol. Anybody remembers what ARP is used for? Yeah? Yeah. So if you want to find out the MAC address for IP, or actually the other way around as well. If you want to find out the IP address for a MAC, you can use ARP. So you can send an ARP request saying that, generally, I mean, if you have the MAC address and you want to find IP, you may just send to that MAC address, but you could also send a broadcast request. So you could just send who has this IP address, and then somebody, hopefully that node with the same IP address and MAC address will tell its MAC address, right? So that is ARP. So a generalization of that is what we call neighbor discovery, to find out who has the layer 2 address. So this is more general than just Ethernet. So that is called neighbor discovery. Dynamic home agent discovery returns a single reply. And the second and the final thing is that dynamic means time changing. So whenever you want to find out who can be my home agent, you get a single reply rather than infinite replies. Everybody saying that I am a home agent and I can be your home agent. So those are the 6 major changes, and we will go through them one by one. So first thing is binding update. So what is a binding? A binding is registering with the home address, home agent. So basically what you register, you say to home agent, look, here is my care of address. Any packets coming to my home address, please send them to this care of address. So it has bound that your home address with your care of address. That is binding, right? And every time you change that binding, that is a binding update. And so in IPv6, there is a new extension header. There is a new extension header which is called mobility header. Type 5 means it is a binding update. Each binding update has a sequence number, and the mobile keeps track of the last sequence number for each destination. Home agent performs duplicate address detection, updates the binding cache, and sends the binding ACK. So basically, you send that, okay, here I am, and then the home agent will make sure that this address is not a duplicate address, in the sense that somebody with that address is not already present in the local network. I mean, it's quite possible that you are saying that you are in Germany, but you are also in Washu. So now there is a conflict. There are 2 copies of you, right? So that is why the duplicate address detection is required. So before it registers, it sends a packet in the local network and makes sure that nobody answers it, and then it updates the binding. So this is just double checking that it's not a false, it's not, okay. And then second thing is no network entry, new network prefix, and default router unreachable. So basically what happens is when you move, your host part remains the same, but you get a new network prefix. Because you are in a new network, right? The network prefix has changed, and that becomes your care of address. And then so you accordingly change. Basically you have to find the new default router. Default router will depend upon the new network prefix, and so those are the things that you have to do locally to be able to send the packets under that network prefix, under the new network prefix. So you have a new, because everybody has this host part, which is somewhat globally unique because it came from the MAC, and then the network prefix, which is unique. So basically you can make an address and start using it, right? So basically some of the things that the foreign agent was doing are not really required here, and you can do it yourself. The second thing is route optimization. Previously we used to go back, so the correspondent will always send the packet to the home agent. Home agent will always re-encapsulate the packet and send it to the mobile. Mobile will send a double encapsulated packet to the home agent. Home agent will take out the encapsulation and send it to the correspondent. That is how it was in IPv4. In IPv6, you can just do directly like this. After you get your first packet, you can tell the correspondent, look, I am right here, and this is my new address. You can send me that way, and then you can just talk to each other directly. So you don't have to follow this triangular path. And the way you do that is that you can put an extension header in which you keep the other information. So for example, the packet as it comes from the higher layers, it will have TCP, whatever the TCP packet is, and on the front of it we will put the correspondent address, which is the source address for the correspondent, and then the destination address is HOA. So the packet will come like this, okay? It will come to it is going from the correspondent to the home agent, to home address. However, the IP layer, IPv6 layer, will add a field here. It will put that new care of address here. This is a destination option header. So this is one of those, remember the extension headers, which is destination option, it is only looked at the destination. So the intermediate routers will not look at this header because they know that this header is only for the destination. This is in the IP layer, but the routers don't have to look at all the headers. They only look at the headers which are designed for routers. So this is destination option header, and this has the care of address. So now the packet is destined to the home address. So obviously if this packet remains like this, it will go to the home address, but we don't want to go there. So then after that, the IPv6 layer will switch these two. It knows that this is a mobile IPv6. So on the wire, by the time it gets to the MAC, the packet looks like this on the media. It has the correspondent address as the source address. It has the care of address as the destination address, and the home address goes into this field destination option header. So they have switched. Alright, so now this will be correctly delivered directly from there to there. Why? Because the destination address, as soon as it got out of the host, here is actually the care of address. And the mobile IPv6 does that switching. Now, in the reverse direction, same thing happens. Mobile node responds, actually before all this works, actually you will have to do that mobility binding. As we said, that mobility binding, one thing I should have mentioned there, the mobility binding you can do not only with the home agent, you can also do with the destination. So you could, just like you register with your home agent that I am at this hotel, you tell your correspondent that look, I am at this hotel. So the same message can go there, and then they will remember all this care of address and so on and so forth. Right? So the mobility binding is a general name which can be sent, and that's why it has to remember for each destination it says. So every place you send, you know that what I told them. Anyway, so it sends this packet. Well, again, I mean, you can start the other way around. Basically, the source address would be home address and CN address and so on and so forth, and packet on the media will look just basically such that the addresses are correct, and the home address gets inside. So basically, the packet will always look like the correct, having the correct source and destination address. all right, in both directions. So let's read these lines again one more time. So shortest path in both directions, that's what we are doing. Mobile sends a binding update to the correspondent. So the mobile sends the binding update, so therefore it knows the care of address and it can do all that substitution there. And then the new destination option, so there is this destination option in which there is home address can be put and the care of address can be put. So HOA option is used in all packets. Correspondent replaces the SA with HOA before passing to the upper layer. So when it goes up, the reverse happens. When the TCP receives the packet, it receives like this, and it will basically, it doesn't really know that it came through mobile IP. The TCP will think that the packet came with the source address of CN, the destination address of HOA, and rest of the TCP. So it is kind of invisible to TCP. It is just basically TCP doesn't have to worry about whether it came through mobile IP or regular IP. The mobile IP layer will take care of itself and switch the addresses correctly. Okay, that is route optimization. So just this slide actually gives a little bit more detail of the header types and so on and so forth, but exactly we have finished the discussion on this anyway. Is that the source and destination options are interchanged before transmissions and after reception. In the reverse direction, the header type is routing header type 2 that contains the home address, and the destination and the addresses are changed before transmission and reception, exactly same thing. And if there is no binding for it, then the binding error message will be sent. So for example, here somebody is trying to send this packet, and then the mobile IP doesn't know the care of address, then it will return binding error. Now, so what is the advantage of this putting the address here? See, if you remember in the IPv4, we do something similar, but actually this is your original packet and this is your encapsulated packet, right? So the original packet, we have not completely put the whole header, we just have this address and that's it. And so basically this is shorter than what it would have been if it was in IPv4. In IPv4 we complete two complete headers. Here you only keep the important part of the header, which is the home address. Everything else is used here. So that's the thing. IP and IP tunneling will require 4 addresses, which in case of IPv4 will mean 4 addresses will mean 128-bit times 4. 3 addresses is a big optimization, 3 times 128-bit. Okay, so instead of doing full encapsulation, we use this special header and put the previous information there, and then so that we can use it at the final place. Any question about route optimization? So 2 generalizations so far. Let me just review that. First of all, that you can send your registration mobility update to your correspondents, right? So if you're talking to 5 nodes, you tell them your new location in addition to home address. So they know your, so the location privacy is gone. I mean, obviously they know that you are what place you are in. Okay. So, but it optimizes the path, because if you are really in a far away from home, but very close to the, because generally what happens is when you are far away from home, you are talking more to the people in that area rather than talking to home people, and therefore you end up, if you don't do this, then you end up taking a long route path. Yeah, question.
So presumably if you update your registration with the other correspondent, you have to do that after you transition network. So how does the correspondent authenticate that you are in fact who you say you are?
Yeah, so I'm coming to that. Good point. So there is a security risk here, because anybody can tell that I am in Germany, and then basically all my packets will go to Germany, and then they'll be thrown out there because I am not there. Right? So we have to verify that. I think that is the next one. Return routability procedure. Now, this slide goes with the next one. Unfortunately, this is a lot of security thing here. So I'm not going to really cover the security part, but this is, you can understand this very easily from this slide. So I'm going to explain, just intuitively as to how this all works. Is that when you say that you are somewhere else, we have to make sure that you are the same person who can also receive things at the home. So you have to send two pieces of information. One piece you send directly to the correspondent and say, look, I'm here. Another piece of information you send through your home address. So something has to come from Vashu which says that Raj Jain is in Germany. All right? And then obviously one direct message will go which will say, well, I'm in Germany. And then something which has Vashu stamp on it, so then we know that, yep, both places. If those two things both arrive and make sense, then we know, yeah, this is Vashu Raj Jain. Right? So that's what we do. So the mobile correspondent and the home agent. So mobile sends a message which is called home address test init initialization. Home address test initialization. This message is sent from the foreign place straight to the home agent, and it is encapsulated, as you can see from this thing here. It is encapsulated, so nobody can read it. Basically it goes straight to the home agent, and then home agent unencapsulates that part and sends it to the correspondent. So half of the message came from via the home part. Other message, care of test init, you send directly to the correspondent. So other half came directly, right? Now if these two halves have something in common or they pass some security test, then we know that these came from the same source, right? And the correspondent does something similar. It sends directly, so by using this it makes a key and sends half of the key directly like this, and the other half it sends to the home address, right, which is encapsulated and sent to the mobile. If you get both halves, then you have made the key. You can make up the whole key, right? Once you have the whole key, then you can give the answer. You can say, oh, I got the key and here's the thing. If your key is wrong, obviously they won't understand anything and you won't get any responses. But if your key is right, then the encapsulation will be heard, understood, and verified. So you can say, well, I got it, and they will say, okay, we got it too. All right, so does that answer your question? Right, so what you do is you send two halves, one through the home, one directly, and then the responder also sends two halves, one through the home, one directly. If both of you get both pieces correctly, then you are in business, you can make up the whole key. Otherwise, you won't be able to do that. Now, in terms of security, it uses this SHA and HMAC and so on and so forth. Unfortunately, I don't think we have covered it, so I don't want to cover it for this purpose. But basically, there are techniques for message authentication and for hashing and so on and so forth, which are used to verify these messages. Okay. So I will not actually, I'm not covering the slide number 10, but slide number 9 you should be able to understand, and basically the whole key part of it is that there are just 4 messages sent, 2 from the mobile to the correspondent and 2 from the correspondent to the mobile. And then if both of them get the full piece, then they can send the update, authentication, and acknowledgement. Any question about that? All right. So one more thing you can do is that you could generate some secure addresses, cryptographically generated addresses. So what is a cryptographically generated address? So generally what happens is everybody has a public key, right? You don't have public key, but if you paid enough, you can get a public key, right? You can go to some companies that sell public keys, which is like a certificate. You can get a certificate from some place and say that, yeah, this is Raj Jain, or this is, such and such. Now, if you, so you can, so that is associated with your address, and now you want to associate with some other address, and so this is the way. So they have an RFC which specifies how you can generate an address, and then you can still associate with your public key. So that way somebody can verify, yeah, this is you, because they have your certificate from before. All right, and so a node can generate an interface ID. So it can generate the 64 bits using the public key on the network prefix. So what you do is you take the home prefix, you take your public key and put a context which is a variable, hash all of it, take the first 64 bit, hash, and then end with this quantity here. Now this quantity is all 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, except there are 2 zeros here in the C. C is 12, 12 is 1, 1, 0, 0. So there are 2 zeros there. When you end, those 2 bits become 0. Everything else remains the same. And then you take the first 64 bit of the result, that gives you your interface ID. Why we zero those 2 bits? Because those 2 bits are universal and the group bits we talked about earlier. And so those 2 bits have to be zeroed. 0 means universal and 0 means non-multicast. Now this is somewhat confusing. Every time I teach this bit name, the name universal is just the opposite of what it's supposed to be. When it is 0, it means universal. All right? And the group bit, when it is 0, it means non-group. All right? For groups, that bit will be 1. For non-universal, that universal bit will be 1. So the names should be, one of the 2 names should be changed so that people can understand 0. 0 means should be local really. So that is the local and the group bit. If the local bit is 0, then it is universal. So if that bit is 0, that is universal. So we zero those 2 bits. And mobile node can sign the binding update using its private key. So now with what happens is, with this method, you have a cryptographically generated address. You can use that address because your network prefix is foreign network prefix plus your CGA, and then you can sign it with your private key. So the way public key and private key works is that anything you sign with private key, anybody can verify it using public key. Public key is public, everybody knows that key. So your Microsoft certificate, all our computers have Microsoft certificate built in. So we know this is Microsoft, right? So similarly, there are lots of other addresses which are built into the computer, so we know that this is coming from that place. So if we have somebody's public key, we can verify it. If they sign something with their private key only they know. Okay? So then you can send a request, you can send a binding update which is signed. So then that is an alternative to this return routability procedure where you don't have to go to the home address to verify you. This one works without a certificate and that one requires a certificate. Yeah.
So this generates the lowest 64 bits?
Low 64 bit, yeah.
So I have a question that's kind of related. So in IPv4, your address is not bound to any hardware, so your address has no part in your IP address. So you could conceivably take the server and have an IP address on it, and then if it blows up, you want to change it out. You don't have to have a different IP address because the MAC address aren't changed. How do you? Okay,
let me understand your question. You went too fast. You have multiple interfaces or what?
Well, I mean, so I could have 192.168.1.1 on my computer, and then I can change it and give it to another computer. But in IPv6, they have 2 different MAC addresses. So how do you give?
Yeah. And you cannot give the address. No. Hold on. First of all, Everybody has a globally unique address.
Okay. But I mean, what if I wanted to give somebody the same address?
We are just violating the rule that I just said.
Okay, well, so I guess you can't then. Because I mean, now with IPv4, you could have a machine and physically replace that hardware, and it will you could give it the same IP address. So nobody aside from you would know that you replaced that machine, right? But you can't do that with IPv6.
Huh? Yeah, the only thing is that the DNS will have to be changed. I mean, if you, generally, yeah.
But I mean, with IPv4, you don't have to change the DNS if you replace the machine with a newer model. But so now, if every year you upgrade a machine, you have to update DNS too, because you're
No, hold on. So okay. Okay, no, hold on. Okay, hold on. Two things. So it is not necessary. Okay, it is sufficient, but it is not necessary to use your MAC address as a part of your home, your host part. Okay. The reason it is sufficient is because once you put that, then you get a unique address. You don't have to ask anybody. Right? You could have DSCP, which is allowed. Right?
It's not a requirement.
It's not necessary. It is just sufficient. Right? So yes, you could give the same address as long as it is not one of those MAC generated addresses. Okay. All right. So we understand that two ways to authenticate yourself. One is through the return routability procedure, and the second is to do this cryptographically generated address. And anybody can verify that this address belongs to this public key. All right. Third thing, final thing is fast handover. Fast handover means that you could connect. I mean, it's like basically you could connect very fast, and generally you could even do make before break kind of thing. So what you do is you are moving from AP access point 1, which belongs to the router 1, which means this is a different subnet, and you are moving to access point 2, which is a different subnet, and its router is AR2. Right? So this is access router 1, access router 2, access point 1, access point 2. This is the mobile. It is going to move from AP1 to AP2. Now it will not know anything about the next subnet until it goes there and says, well, what is your subnet address, and give me an address, and so on and so forth, right? That would really break the connection. It will take a long time. So the fast handover is that you can ask that question from access point 1. Because you are talking to access point 1, before you go to access point 2, you could ask access point 1, who is the router for access point 2? Right? And if the access point 1 knows about fast handover, it will somehow ask somebody else and somehow get you the answer. So what it will do is it will say AR2 is the router and 2 is the prefix. Right, so this, by the way, the names below the lines are what we call the message name. So it will send a proxy solicitation whose English meaning is who is the router for access point 2. The real name is proxy solicitation. So it will send a proxy solicitation to AR1, sorry, AP to AR1, sorry. I'm sorry, it is not going to AP1, it is going to AR1. Who is this router for AP2? And it tells you the answer that AR2 is the router and N2 is the prefix. So the router is answering this. At the same time, the router will send a message to AR2 and say mobile wants an address, so that message is called handover initiate. And so the AR2 will send the response back to AR1, yeah, he can use or she can use address X. And then it will say, what address can I use? At that point, this already had the answer, and it will say you can use the address X, and then it can directly talk to, as soon as it moves to AP2, it can directly talk to the router 2 and says, well, I am address X, and now once this handshake is over, then they can start sending the packet. All right. So basically, you don't have to connect to the router before getting the address. That's the point, is that your previous router can give you the new address. And it can give you the new address by asking the new router. So they have added these messages called proxy solicitation, proxy advertisement, handover initiate, handover ACK, fast binding update, binding ACK, fast neighbor advertisement, fast neighbor advertisement at ACK. So all these messages, once they are implemented, we say that this router implements fast handover, or this mobile implements fast handover. And in that case, when you break, you only have one round trip here. When you go to access point 2, your first round trip is this, and then you can start sending the packets. All right, so this is actually exactly what I have already told you. Let me just double check that there is nothing new here. Yeah, solicitation, advertisement with at least one prefix, and then it sends a message, AR1 sends to AR2, AR2 does the DAD. So that was one thing I didn't say, that the AR2 does check that it has not given the address to somebody else, and then it sends the address. So that is duplicate address detection, right? And then it gets the binding update, binding ACK, and mobile send the fast neighbor advertisement, and so on and so forth. Everything else we have talked about. And it can also use CGA. CGA is the cryptographic generated address to avoid high and high ACK. So high is this last message, and let's see, HI, handover initiate and handover ACK. So this is where it gets the address, right? And the mobile can generate an address once it knows the new prefix. As soon as it knows the prefix, it can generate an address which is unique in that prefix for itself. So that this part is not required. All right. So two more modifications. This is one, and the second one coming after this. First is hierarchical mobile IP. So hierarchical mobile IP is based upon again a solution to this whole round trip thing, triangular thing, is that if you are in a foreign country, you don't really want to talk to your home agent all the time here. So can you find an agent in that country which acts like your home agent? And so actually instead of calling them home agent, we call them anchor points. So you can find an anchor point in a foreign country, and that is, so you will have a hierarchy of anchor points, and that becomes hierarchical mobile IPv6. So this is mobile, and this is the regional care of address. So this is a regional mobility anchor point, and so it sends a binding update to the regional anchor point. It tells the agent locally that I am here. So this is the binding update 1, BU1. Then it also tells the home agent. All right. Now you will have a triangle, and it can also tell the binding update to the correspondent. If it sends to the correspondent, then basically if you want to perform any kind of return routability procedure, you don't have to go to the home agent, you can do it right here. Or if you want to do CGA, obviously you don't need to do even that. So basically you inform three people. You inform your home agent, you inform your local anchor point, a regional anchor point, and then you can also you can also inform your correspondent. Okay, so the idea is that you don't have to do everything through the home agent. You can do something through the regional mobility anchor points, and so that is called hierarchical mobile IP. Right, that's the whole idea. That's a regional COA. Second concept, which you will hear if you talk about mobile IP, is proxy mobile IP. And in proxy mobile IP, the hosts don't change at all. So they don't implement any mobile IP stuff. They just talk like if they are normal IP. However, the access points do all the work for them. So if you buy an access point and it says that this is mobile IP enabled, then they could be doing proxy mobile IP, where they would do all the registration and whatnot for you. So here is an example. There is an access point at home. When the mobile node is connected here, it is connected to this access point and talks to the router. When it moves, it talks to this other access point, and this also happens to be mobile IP enabled, actually PMIP enabled, which means proxy mobile IP enabled. When it goes there, and this one doesn't really know that I have moved, it doesn't know about mobile IP, so it still uses its old address. All right. So this access point looks at the network prefix and it says, well, this really belongs to WashU. This is not here. It has the whole world's database. All right. So it belongs to WashU, and it also knows in WashU who is the home agent. So it informs the home agent that this address is here, and then it does everything else that the mobile IP would have done. So this whole thing combined would become a mobile IP agent, basically. And so this will keep sending and receiving packets as if it was still at home. But this access point will change the addresses. So when the packets go on the network, they will have the correct source and destination addresses and whatnot. Okay. Now, not everybody can remember the whole world thing, right? That would be just too much to imagine that every access point will know everything. So what we do is, we have some people know some things. So they just know a little bit, whatever is the cache, but there are some access points which know everything. So there is authoritative access point. This access point has all the information. So if it doesn't know about that one, it can ask the authoritative access point, and the authoritative one will look up its worldwide database and say, okay, here is the home agent for this network prefix. Okay, this is similar to DNS. In DNS, when you ask for a name to address resolution, you can ask your neighbor, they might know it, but if they don't know it, you go to the authoritative DNS, which resides right in the company where the address is located, and they will know it for sure. All right. Now, the reason I talk about proxy mobile IPv6 is because the cell phone companies are adopting IP. And when they adopt IP, they want to use proxy mobile IP. They have suggested that we will use proxy mobile IP. So the mobile IP is right now not used. As I said, we have discussed so much, but I have never seen one. However, the cell phones, when they start using this, then they will use this method where the cell phones themselves will not know what IP address, and they just use one IP address, and then the cell towers will take care of the details. Okay, makes sense? Let's just double check here. So IP, we have already discussed all of it, but I'm just going to double check. IPv6 nodes have 128-bit addresses, the subnet part and the host part. PMIP enabled access point cache a database of home agents for all subnets that they support. Authoritative access point keeps the latest copy. All access point can ask the authoritative for the correct information. When a node connects to the access point, it looks at the subnet address of the mobile node. Who looks at? The access point looks at. And it realizes that this is from foreign network. finds the home agent, registers the address with it, and all packets coming to the home address will be forwarded to the access point. Okay? So basically, so even though, I mean, in that environment when this is implemented, we will not see mobile IP, but it is in the background. It's working in the background. Right now, I don't think this exists in the real IP network, in the sense that I have not seen the mobile IP advertisements and things like that, and so on. So anyway, that finishes mobile IP, and these are the 6 key points. First thing is that there is an extension header, mobility extension header, MH, and we talked about MH type 5, MH type 4. So in that, there are different messages. And then you can also do optimal route, avoid the triangulation by directly telling the correspondent, doing the what we call binding update with the correspondent. You can do it securely using return routability. There are 2 ways to do securely. One is by using return routability procedure, and the other is, what are the 2 methods of doing securely? Addresses, yeah. Your address itself can be verified by somebody else by looking at your public key that this is the address generated by this person. And then there is a fast handover, which allows you to get the new address before you get to that network. And again, there are 2 ways to get that new address. One is that you go through the router, and the router goes to the router and finds it. Other one is to just do the cryptographically address. Then there is hierarchical mobile IP. In hierarchical, basically you can make somebody local as an anchor point rather than going through the home agent for all these procedures. And then there is proxy mobile IP. In the proxy mobile IP, the access point do the job for the mobile. Okay. All right. So you can read about proxy mobile IP on the Wikipedia, mobile IPv6 on the Wikipedia. Actually, so these 3 are actually in addition, but not really required here. But there is a mobile VPN and VPN and proxy app. So anyway, so these 2 you might want to read: proxy mobile IP and IPv6 there. There is a document that I found on the net from Cisco. It's called Configuring Proxy Mobile IP. So Cisco implements it, obviously, and then this document was really readable. And the Proxy Mobile IP slide came from there. These are the RFCs, mobility support in IPv6, Proxy Mobile IP, fast handover, hierarchical mobile IP. So those, the homework is to read 3775. 3775 is the first mobile IPv6 thing. So mobility support in IPv6, 3775. I want to make sure that you read it and make a list of 9 fields that are stored in the binding update list entries. So once you read it, then you will know what the answer is. Okay. And this is the list of the rest of the RFCs. You don't have to read any of them, but just in case if ever you do any work on that field, then you know what to find. And the list of acronyms. Okay.